Section 10.3, continuity. All right, I'm going to give you the very basic definition of continuity, and then we'll go over the calculus. Continuity is simply this. A function is continuous if you can start to graph it, and you can graph the whole thing without ever picking up your pen. If you have to graph it, and then you have to pick it up to maybe jump over a hole, or to cross a vertical asymptote, that's not continuous, right? So continuous is just, can you graph it without picking up your pencil? If you have to jump up and over something, that's not continuous at that point. All right? Now, to make this rigorous, we will give you the three pieces of the continuity definition. And this is, we start with continuity of point, then we'll work our way up to intervals and things. So, first off, a function is continuous at x equals c if the following three things occur. Let me go back to blue here. Number one, the limit as x goes to c of the function exists. Okay, so we actually get one that exists, not infinity, not negative infinity, and not dne. Number two, the function value, f of c, exists. And number three, the limit as x goes to c of f of x is equal to the function value, f of c. So remember, we've seen pieces where these things can sort of fail on their own. So for example, let's say I have this graph here. Here's 3. All right, and this is 2, and this is 4, maybe. Is this function continuous at x equals 3? No. The answer is no. Which of the three conditions above does it fail? Yeah. This graph fails the third condition. Let's check it. Condition 1 is the limit exists. What is the limit as x goes to 3 of this function? The limit is 2, because we're coming in on both sides. We get a 2. Number 2, what is f of 3? F of 3 is 4, because the function value is where we have the solid dot. And then number 3, does the limit value equal the function value? No, it doesn't. The limit value is 2, the function value is 4. So this function is not continuous at x equals 3. In fact, we have a word for that. Discontinuous. Write that down. Discontinuous. Discontinuous. Okay. Questions over what each of these three conditions are saying, right? The first one is the limit exists. The second one is the function value exists. And the third one compares their actual values. So not only do the limit and the function have to exist at that point, they have to be the same value. All right, go ahead and work example 1 with your partner on the next page. Now, if it's discontinuous at that point, then you need to state the reason why it's discontinuous. One of those three things has to fail. If it is continuous, then you need to show all three steps, right? The limit exists, the function exists, and the function value equals the limit value. All right. Take a few minutes to do that with your partner. C at the end. Yeah, right here. So let's use technical here. We're writing this here. Okay. If you take a look does the function yeah. Is there a solid part of the graph where x equals 0? This one you have to check all of it.
I know, but so the reason why this one is
So the three conditions you have to do.
Oh yeah, C. I'm fine.
That's not enough. You have to check to see if there's some other solid somewhere.
All right, how are we doing?
Got it? Yep. Think about this. Now, if it's discontinuous, you just need to state the one of the 1, 2, 3 from above where it failed. If it is continuous, you need to show all three parts. So no. A is no. The limit would be where the function leads to. That's okay. That's okay. Right. You're just looking to see where the graph would go. The whole is really just an entry point before the other branch. So to a limit, it's got a whole that's the function value, exactly. Yeah. So the next part is, does the function exist? Correct. But, okay. Just because this is a whole doesn't mean the function doesn't exist. But you're looking at it from a but let's Just because there's a hole here doesn't preclude there being a solid out somewhere else on the same line.
It might be higher up.
It might be higher, it might be lower. Like this one right here. There's a solid right there. There's a hole there.
Which makes it low, correct? Because it's being valued.
Well, let me ask you this question. So for x equals 2, the function value of 2. Because you have a hole right here, it doesn't exclude this being the value, right? If the value is the same, because that example I drew, the limit is the function. So that makes sense. All right, let's check them. Okay, let's see. Daniel Messina. Number 1. Is the function f continuous at x equals 0? Yeah. I don't think it's yes. I think it's no. Let's see. Who's got this one?
FC doesn't exist.
Yeah. Yeah. So you check the three criteria, right? Number 1 is the limit. So let me do it with this one. The limit as x goes to 0 of f of x. Does that exist? Yes, that's actually 3. Because the open circle here, the hole, that's okay. We're just coming into that value from both sides like that. So the limit exists. Number 2 would have to be that f of 0 exists. Does it exist? It doesn't exist. It's undefined. And so therefore it's not continuous. So no, f of 0 is undefined. Okay, let's see. B, Nicholas.
Discontinuous? No.
Yeah, this one is not continuous. What is the reason for the discontinuity?
Fx doesn't equal fc.
Let's see. Well, I think there's a problem before that. So for this one, what is the limit as x goes to 2 of f of x? Well, it's 1 if we were doing a left-sided limit. It would be 3 if it were a right-sided limit, but this is the whole limit. We've got to have the whole limit. And so that limit does not exist. Because it's 1 on the left and 3 on the right. So the limit does not exist. So no, limit as x goes to 2 does not exist. And then C, is f continuous at x equals 1? Yes. And here we need to show all 3 parts. Now, really what you can do is you can just show the last one. And you can incorporate everything else. Because if the limit exists, then what is it? Well, it's some number. And then if the function value exists, then it's some number. And so that's what we get. So here's what we usually do. We just do the limit as x goes to 1 of f of x is equal to, what is the limit? It's 2, which is equal to f of 1. You just make that statement and you're good to go. That one statement embodies all 3 parts. Because saying that the limit is equal to a number implies existence. Saying that the function value is equal to this number implies existence. And they're all equal, so we're good. All right, I think some of you are still having some problems with limits. Like looking at the graph and telling when the limit is still there. Just for me walking around and helping. So be sure to work on that whenever you do the homework tonight. Let's do the continuity on an open interval. I tell it. Let's just stop. We'll stop there for today. As a reminder from yesterday, we had continuity at a point. Continuity at a point is defined by three things. That is, the limit as x goes to that point C of the function exists, the function value exists, and they are the same things. You can have examples where, for example, the one we did here at the bottom, the limit exists, the function value exists, but those two things are different. So that's something to watch for. Then we did this example with continuity at a point. We talked about all of those. We continue today with continuity on an open interval. And we have the following. If f is continuous, at every point in the open interval a to b, then we say that f is continuous. And by the way, the abbreviation for continuous is CTS, as seen there, on a to b. So a quick reminder, what does it mean to be an open interval? Open interval means we have a sort of a segment, but we do not include the endpoints of those segments. So the open interval a to b is every real number between a and b, but it doesn't include a, and it doesn't include b. Also, from algebra, you might remember that if you use a parentheses on the left or on the right, that means we do not include that endpoint. In order to include the endpoint, we would use the closed notation, and that's a square bracket. So just a reminder of those notation type things. The bracket represents inclusion of the endpoint, parenthesis does not. Okay? And then we had one other item, make sure that we get this in our notes. Discontinuous, of course, just means that it is not continuous. All right, so that's what we're looking for. We're now looking for continuity on intervals. So a function is continuous on an interval if it is continuous at every point inside of that interval. If we look at example 2, determine the intervals where each function is continuous. The easiest thing to do is to look for the discontinuities. Okay? If you can find all of the discontinuities, then every place where there's not a discontinuity is going to represent intervals of continuity. Let's look at example A. F of x is equal to x squared minus 25 over x plus 5. We're looking for where this function would be discontinuous, and that happens where the denominator is equal to 0. What value of x makes this denominator equal to 0? We get 5. So this is a discontinuity, all right, discontinuous. So everything other than negative 5 is going to be a point of continuity. We're going to create intervals around that. If we were to draw the number line, then the only bad point would be right here at negative 5. I'm going to represent that by saying it's an open circle there. And then the points that do work is everything else that I'm shading in. So all of this on that side, and all of this on the right side. And now we take this interval, or these two intervals, and we create the solution. So it's everything left of negative 5. So that would be negative infinity to negative 5. It's open at the end point negative 5, because it includes everything up to negative 5, but it doesn't include negative 5. And then negative 5 to infinity, that's this second half here. Bless you. And when you take two intervals and you want to put them together in sort of a string, we use union. Union is this little cup-like symbol, like that. It's not a U. It's just a little cup. When you go to enter your homework solutions on My Math Lab, you'll find the little cup symbol on the left side in that palette. All right, you just click on that. In the program that I use to type up your test and your notes, and that makes all the math symbols, this is called a cup. You may be able to enter this symbol by typing \CUP. I don't know if that works, but you can try that and see if that works. That'll save you from having to go from keyboard to mouse to keyboard.
What is it for?
It's for the union symbol, to create this symbol. Is that what you asked?
Like, what does it mean?
It means we're going to put these intervals together. We're going to use both of them. So technically, it means that the x values where this function is continuous is either in here or in here. And you're just putting them together. Okay. All right. Example B, g of x is equal to x squared plus 3x minus 4 over x minus 1. Where would this function be discontinuous? X equals 1. So we can form the interval here. And here's 1. And we'll just jump over 1 like that. We're going to use all of this other part that's shaded. So that would be negative infinity to 1 union 1 to infinity. What about C? Where's the discontinuity? It's x equals 3. So here's a number line with x equals 3. We'll jump over that. And that creates the interval negative infinity to 3 union 3 to infinity. Let's add a couple more of these here that's not listed. How about j of x is equal to x over x squared minus 4. Where is this function discontinuous? 2 and negative 2. If you don't see that it's both 2 and negative 2, what you can do is you can set the denominator equal to 0, and then this factors as x minus 2 and x plus 2, because x squared minus 4 is called the difference of two squares. We talked about that already. Then you would set each factor equal to 0. And we get x equals 2 and x equals negative 2. So this time when I draw the number line, I need to put in both negative 2 and positive 2. So we're going to have here and here and here. Based on the number line I've drawn, how many intervals will make up this solution? Should be 3. Yeah, 1, 2, and 3. So we'll have negative infinity to negative 2, union, negative 2 to 2, union, 2 to infinity. Questions so far? One more side note. Remember that whenever you're using negative infinity or positive infinity, you always use the parenthesis. You never use a square bracket with infinities. Okay. In addition to continuity on an open interval, we have continuity on a closed interval. It gets you some. The definition of continuity on a closed interval, in order to do that, we need a couple of more definitions. To be continuous on the right, we're going to define what this means. Continuous on the right. You basically take your three conditions for continuity at a single point. Two of those had limits in them. You change those limits to right limits. So the limit as x goes to c from the right of a function, if that is equal to f of c. So you make the adjustment in the definition of continuity at a point. You just change it to a right limit there. Same thing for continuity on the left. You change that limit to a left limit. So you have the limit as x goes to c from the left of f of x equals f of c. Once you have that, then we can define continuity on a closed interval. So, continuous on the closed interval a to b. In order to have that, you need the following three things. Number one, you need continuity on the open interval from a to b. So that takes care of all the points in the middle of the closed interval a to b. And then the only thing we have to worry about is what happens at a and what happens at b. So, let me draw a picture so you can see what's going on here. Here's a, here's b. This function is continuous on the closed interval a to b. It's obviously continuous on everything between a and b. And then look at a. What happens when we get closer and closer to a? What about the limit? Well, this is some value. This is some y value here, and this is some y value here that we don't know. The question is, if you take the limit as you come in from the right here, so this is the right limit, does the limit value equal the function value? Yes. Yes. The limit as x goes to a from the right side does equal the function value at a. So that is continuity on the right. So continuous on the right at x equals a. And what about as we come into b here? We come into b from the left. So what is the limit as x goes to b from the left? Is it equal to the function value? Yes. So this is continuous on the left at x equals b. So you have to have each of those three components to be continuous on the closed interval. You could certainly make some sort of statement about a half open and half closed type interval as well. But in general, once you get both of these, then you're good to go. Let me give you the contrasting example here. Suppose you had this graph here. Here's A, and here's B. And it was open here with the value there, and then comes here and there's the value there. This function is not continuous on the right at a, because the limit as x goes to a ends up at this y value, whatever this is, but the function value is down here. So that is not continuous on the right. What about it at b? Is this function continuous on the left at b? Yes, because the limit is equal to the function value. So if anything, we could say that this function is continuous on this interval. Open at a and closed on b. You could say something like that if you wanted to. All right, let's look at example 3. Determine the intervals, open, closed, or otherwise, where the function graph is continuous. And to do this one, we'll just go from left to right here. So what can you tell me about the continuity at -2? It's closed because it is continuous on the right side of -2. So we can have -2 here. Now, starting from x equals -2, how far can you go through the graph from left to right until you run into a problem? You can go to 0, right? If I'm here, everything is hunky-dory until we get to x equals 0. What can you tell me about the continuity at 0? Is it closed at 0 or is it open? It's open because we don't even have a function value at 0. So it can't possibly be closed on the left. What about on the right side of 0? Is it open or closed? It is open. And how far can you go until you reach a problem? Yeah, you can go all the way to 2. Is the continuity at x equal 2, is it continuous on the left?
No.
Correct. What is the limit as we go into 2 from the left? 1. What is the function value?
3.
The function value is 3. The function value is way up there. Yeah. So coming in from the left side, the limit is down here, but the function value is up here. You have to disregard everything else that you see. You're just looking at the left side and the function value. We're not even on the right side yet. So the function value is up here, the limit is down here. That is not continuous on the left. So it is open there. And now, what about continuity from the right at x equals 2? The limit goes to 3, the function value is 3. It is continuous on the right. What about as x goes to 3? Yeah, it is. It's not continuous on the left, so it's open.
Why did we stop at 1?
At 1, there was no problem with 1. No problems at 1. It is continuous at 1, but it's also continuous on both sides of 1. So you just keep going. It's also continuous at 1/2 and 1.5 and everything else. You don't stop until you get to a problem. This is not a problem.
Is it just an open interval?
Say it again.
You usually stop at like an open interval?
Yeah. Yeah. Well, either an open interval or where you're going to have a discontinuity.
Okay.
So we had a jump here, that was a problem. We had a hole here, that was a problem. That one is continuous at that point, so that's not a problem. Yeah.
Maybe.
Yeah. Yes.
The point 0, why wouldn't you bracket together those first two intervals?
Mm-hmm.
Put a u.
You can. Yeah, a lot of this is sort of bracketed together. The reason I don't do it on this one is there's something else going on here. If you tried to use the U with the union with 0 to 2, union 2 to 3, and it's closed at 2, then that would be continuous. You could sort of simplify that as continuous everywhere. Because one of them says I go everything up to 2, the other one says I go everything up to 2, including 2, which is everything around 2, which is not what we mean here. Here we're just doing, this is sort of half open. This one is open, this one is half open. So I would leave those separate. If you wrote it that way, I guess that would be okay. But you got to make sure that your readers understand that you don't mean to say that it's continuous from 0 to 3. Yeah, does that make sense? You see, like if we put these two together, even when we put these two together with union, it doesn't include 0 because this endpoint didn't include 0, this endpoint didn't include 0. If we try to put these together, it does include 2 and everything around 2, which would make someone think that it was continuous at 2. It's not continuous at 2.
So you can put the first two together.
You cannot put the first two together. Well, you mean with a union? I wouldn't do it. On a question like this, where you're working with potentially open and closed and things like that, I would leave it alone. I would continue to use a union on these that are just strictly open. Or if it was closed on one end, that the interval before it didn't have the other piece that went right up to it. Does that make sense? Yeah. Yeah. Okay. All right, so how do you know which functions are continuous? Well, we have a chart. In this chart, we're going to give you the details about which functions are continuous and which ones are not, and what you should do to find their intervals of continuity. The first one is f of x is equal to k, which is a constant. That function is continuous for all x. So you would write negative infinity to infinity. Number 2, f of x is equal to x to the n, where n is a positive integer. So x squared, x to the 5th, things like this. This is continuous for all x. So negative infinity to infinity. Polynomials, we talked about polynomials a little bit. Those are expressions that have x to positive integer powers. And then they have coefficients. The coefficients can be fractions, but you can't have fractions with the x's. Right? These are continuous for all x. Number 4 is a rational function. Rational functions are polynomials divided by polynomials. These are continuous for all x where q of x, the denominator, is not equal to 0. So again, you'll do what we did in some of the previous examples. You'll find where the denominator is equal to 0 and exclude those points. Then everything else is part of the intervals of continuity. 5 and 6 are related. 5 is when you take an odd root. So this is the nth root of f. N is if it's a positive and odd number, then this is continuous for all x, where this inside function f of x is continuous. So having an odd root does not really change the situation. You have to look at the underlying function, what they call the radicand, right? The function inside the radical, to determine what the continuity would be. And then number 6 is an even root of a function f of x. This one is a little more complicated. This one is continuous for all x, where, first off, f of x is continuous, and f of x is greater than or equal to 0. So because it's an even root, remember you can only take the even root of positive quantities. You can't take even roots of negatives. When you took college algebra or the like, you remember you had that I thing, right? The square root of negative 1 was I. We don't do that in this class. So we just say it doesn't work. Okay. All right. So those are the conditions. On example 4, I'm going to let you work that as group work. So there's 4 examples there. Go ahead and determine the intervals of continuity. Cite the rules 1 through 6 from above that you're using to determine those intervals of continuity. Answers to example 4. We'll call on some people here. Let's see. Ross, on A, what type of function is A?
Number 3.
Number 3, it's polynomial. Right. Number 3, polynomial. And where are polynomials continuous?
Negative infinity to infinity.
Everywhere. Yay. Okay. All right. Yes. Very good. All right. B. Raquel. How do you say your name?
Raquel.
Raquel. That's what I said. Okay. Raquel. Where? What type of function is G?
Rational function.
Rational function. And what do we do to solve and find the continuity of a rational function?
I can't remember what it's called, but you're gonna get x plus 1. Let's see. Yeah, solve for x.
Yeah. Take the denominator, set it equal to 0.
Yeah.
Solve for x. So this one factors. So it's x and x, 13 and 1 minus and plus. Then set each factor equal to 0. So x equals 13 and x equals negative 1. And then you want to form the intervals around this. Okay. Now, drawing this number line, you don't have to do that if you don't want to. But I'll tell you, here's one of the big mistakes that I see students make on this particular type of problem. They see 2 numbers. They see 13 and they see negative 1, and they put down the interval negative infinity to negative 1, union 13 to infinity. They put it together, but this is wrong because what are you missing? You're missing the middle, right? You got to include the middle. So you will do yourself a favor if you will draw the number line interval, because you can actually visually see the number of answers there are. There are 1, 2, 3 answers right there. So it's negative infinity to negative 1, union negative 1 to 13, union 13 to infinity. Okay? Again, it is superficial and it's up to you if you'd like to do that. Very good. All right, Mark, number 6. What type of function? What rule, at least?
Rational and then the odd function.
Yeah, it's a number 5. We have an odd root. And then the rule for number 5 says to piggyback on whatever the inside type function is. The inside type function is rational, so that's a number 4, rational. To solve a rational, take the denominator, set it equal to 0. The denominator is x minus 1, so x is equal to 1. There's only one, oops, wrong. So 1, and so it's everything around 1. So this is negative infinity to 1, union 1 to infinity. Question? Yes. Weston.
Can you have? I didn't know. Can you have a negative number as a square root?
You have to be careful. You can't take the square root of a negative number, but with a certain function, you could use negative x's that under that function they then become positive, and then it's a square root. Now this is not a square root. This is a fifth root. Right? So do you understand the meaning of fifth root? Right? So for example, you know how when we have square root, it's Like the square root of 4 is 2, because 2 times 2 is 4. The fifth root of 32 is 2, because that's 2 times 2 times 2 times 2 times 2. 5 2s, right? 2 to the fifth is 32. When you have an odd root, you can take the fifth root of an odd root. So, for example, the fifth root of negative 32, that is perfectly legitimate. That is negative 2. You can take odd roots of negatives, yeah, because of the pairing, right? If it's an odd number, then the negatives would pair up, 2 there, 2 here, and you'd still have 1 left over. Well, if it's odd, you always end up with pairs and then 1 left over. So it always works. All right. D was sort of difficult. Who got D? Well, let's have that one. And I'll tell you this. I like it. I like that you want to give me what you think is the wrong answer. Because you know what? And this is the truth. If you learn nothing else in this class, this is what I want you to take away from this. You will learn more from making mistakes than you ever will from getting things right every single time. I guarantee it. Guarantee it. Write that down. Write that down. Write that down. You can even tweet that and make that your status and everything. All right? Okay. All right. What'd you get?
So I did the difference between squares, and so I got it'd be discontinuous 3 and negative 3, but since technically it has to be greater than or equal to 0. The 3 would be the only one that matters. So I got open interval 0, 3, union 3 to infinity.
Like that?
Yes.
All right. Why is that wrong?
Is it because it's not a closed interval at 0? Is that greater than or equal to?
No, you said something that was very good. It was very wrong. What was it? What did he say that was wrong when he was describing the answer?
The negative 3 doesn't matter.
Why not? What did you say right after that?
Because it had to be greater than or equal to 0.
Right. Okay. Because what's under an even root has to be greater than or equal to 0. Now the problem is it's not the x that has to be greater than or equal to 0. It's the expression x squared minus 9 has to be greater than or equal to 0. So it's not the individual x, because take, for example, what if x in this case were equal to negative 5? Then negative 5 squared minus 9 is equal to 16. And that's positive, and you can take the fourth root of 16. It's actually 2. So that's okay. So actually negative 5 is a valid number. It works fine. So what's going on? What do we have to do to fix this? This piece, by the way, up to this part, this is correct. You do need this piece. But the result is not right. What do we have to do after that? I'm going to give you a little preview of what's coming up next. One thing that you can do, there are several ways to do this, but one thing you can do is graph this function. That is the inside function, which is y is equal to x squared minus 9. Now, let's keep our eye on the ball here. This is the function we're trying to find where it's continuous. So this is the piece that we want to be positive or 0. It's okay if it's 0. So if I graph this inside piece right here, x squared minus 9, you know that this is a parabola because it's x squared. We have a vertical shift of 9 down, and it looks like this. And you know what these points are because you found them over here. When you set it equal to 0, that's the same thing as finding the roots. So that's 3 and negative 3. And now you just interpret what does it mean to be positive. Positive is above the x-axis. So this function is positive, yeah, again. And it's the x's that we want. So what x's are part of this piece right here?
Below negative 3.
Anything less than negative 3. What part of the x's make this piece positive? 3 to infinity. So it's negative infinity to negative 3, 3 to infinity. The middle, right? This middle gets excluded because where's the graph here in this middle part? It's below the x-axis, and therefore those values are negative. Final question is, do we include negative 3, and do we include positive 3? The answer is yes, we do. Because the rule was it has to be positive or 0. Well, it's 0 at negative 3 and positive 3. So what do we get? Negative infinity to negative 3, union 3 to infinity. In fact, let me log in real quick and show you this one. Oops. So if we use the Desmos calculator, this would be x squared minus 9. One of the symbols for fourth root is just to raise it to the 1/4 power. And there you go. Checker mode. Let me graph y equals x squared minus 9. All right, the red graph is the graph that we are interested in. Notice that the graph it's not even defined inside this interval. Right? The graph of the function that we are talking about is this red graph. It actually stops right here at negative 3, and then we have pieces over here. 3 here. We have pieces here. We have a completely undefined function here. Nothing there. And that's because on the original graph, right, it was below the axis here, and then above the axis almost. All right. Questions over that? Okay.
First question.
Yeah.
Oh, wait, never mind.
Okay. All right. So the technique that I used to solve that last one is the Sine Cart deal. Basically, we did a graph and we found the Sine Cart. We're going to talk about this more explicitly now. And here is the rule to know right here. If f is continuous on the open interval from a to b, and it's not 0 for all x in a to b, then one of two things has to happen. Either this one or that one. Okay? And those things are f of x is positive, right, greater than 0, for all x on a to b, or f of x is negative on a to b, less than 0. Let me show you what we mean by all this here. We have these two conditions. We have f is continuous on a to b, and we have that f is not equal to 0 on a to b. So here's A and here's B. Suppose I know, and we do this just, we just got to pick a side here. We're going to start here on the positive side, right? So positive and then negative down here. So there's f of A. Is it possible for me to get from here to someplace down here? Can I get from here to here? Can I do this? Is that possible? Michael, why is that not possible?
Can't equal 0.
Can't equal 0. It would be 0 right here. So this is not possible. What's your other choice for getting from this point to this other point? we have a jump. How about this? Why not? It's not continuous. So, can't be 0, has to be continuous. Does everyone agree that there's no way to go from here to here without breaking one of these two rules? That's my only choice. What about a vertical asymptote? Okay. What about goes up to infinity, comes up here, and does it? What about that? Not continuous. Not continuous. So there is no way to get from here to here without breaking one of these two rules. So the only thing that can happen, let's say that we had a point here on the inside. The only thing that can happen on this interval is for it to stay on one side of the x-axis. If it has to stay on one side of the x-axis, then it's either all positive, one scenario, or if it started down here, it's all negative. All right. And the crux here is continuity and not being 0. Okay? So what that means is the points where it is discontinuous form a place where we could change, right? And the points where it's equal to 0 form places where we could change. Just like in the previous function, here was 3 and here was negative 3. These are equal to 0, so these are points where it changes from negative to positive, negative to positive. But it had to go through 0. But you can also change when you have jump discontinuities as well. All right, so that is the key. If it has to be continuous on an interval and not 0, it's all positive. This one, all positive. Or it is all negative. That is the key to doing sine charts. Right. So to find where it could change from being positive to negative means we have to find where it is equal to 0 and where it is not continuous. So that way I don't break this rule here. All right, example 5 says, where is x squared minus 2x minus 3 over x squared minus x positive? Where is it negative? And then we'll create the sine chart with the appropriate partition points. All right, so what are partition points? Partition points are where f is equal to 0 and f is discontinuous. So the partition points are where the function is equal to 0 and where the function is discontinuous. So to find the zeros, we set the function equal to 0. Now I'm going to show you this, and then from here on out we'll probably take the standard shortcut here. To solve this, you would cross multiply. The only thing to cross multiply is the denominator to the right side. When I do that, we get 0 times x squared minus x, which is x squared minus 2x minus 3 equal 0. So essentially, setting the function equal to 0 results in, if it's a rational function like this, then that's the same thing as just setting the numerator equal to 0. So that's the standard shortcut. Instead of taking the whole fraction equal to 0, we'll just set the numerator equal to 0, because the denominator was going to cancel out anyway. All right, how do we solve x squared minus 2x minus 3 equals 0? Suggestions? Factoring, 3 and 1, negative and plus. So this is x minus 3 equals 0, x plus 1 equals 0. So that's x equals 3 and x equals negative 1. So those are our zeros. All right, keep track of that. Over here, let's find the points of discontinuity. To find where a rational function is not continuous, we take the denominator and set it equal to 0. So this is x squared minus x equals 0. Factor out the x. So that's x times x minus 1. Set each factor equal to 0. So this is just x equals 0. This is x minus 1 equals 0. And so that's x equals 1. And these are the points of discontinuity. Okay. Yeah.
So you said if you find the zeros, you set the numerator to 0, and you find the point of discontinuity, you set the denominator to 0. That's not always the standard thing, right? Because there's been a few times where you do the denominator.
Well, we were finding the zeros of the denominator.
Oh, okay.
Right. So technically, these are the zeros of the denominator. These are the zeros of the whole function. Yeah. So.
Can you explain what the zeros of the denominator determine? Like, on graph?
Mm-hmm. They're either holes or vertical asymptotes. Yeah. So there'll be the points where it's discontinuous, and then from what was it, section 2 or something like that, you take the limit and then you figure out if it's a hole or a vertical asymptote. Yeah. Yeah. But because it's a discontinuity, because it's a vertical asymptote or a hole, that represents a point where it possibly might change signs, which is what we're interested in on this part. We want to know where it's positive or negative. If it's a vertical asymptote, we had examples where both sides went up to the top. That doesn't change a sign. There's positive and positive on either side. But we had some that did this deal, where it was positive and then negative. So that's a sign changer. All right. Now, let's do the sign chart. You want me to use my line tool? Okay, I'll do it for you. Yeah, let's see. Oh, wait, line grid. What is this? Oh, this could be good. No, it's not good. All right, that's okay. All right, so let's throw in the points that we have here, the partition points, in order. So we have -1, 0, 1, and 3. Now, what we know is that these are the points where the function is 0 and where the function is discontinuous. That means if I pick a single point inside one of these intervals, and I determine that it is positive, let's say, then that means every point inside of the interval is positive. Because the only way you can change sign is to go through a discontinuity or a 0. If you're in between one of these two numbers, there are no zeros left, and there are no discontinuities left. So everybody inside this single interval must be the same sign. Okay? That is the crucial point here. Once you have established what the zeros and the discontinuity points are, then everything inside the intervals created by them are going to be the same sign, because there's no way to switch it and change it. So that is what we do. We do some testing. So we're going to pick some points inside these intervals to test. Here's the interval from -∞ to -1. I'm going to test at the point -2. And to test it, all you do is you just plug it into the original function. So f of -2 is -2 squared minus 2 times negative 2 minus 3 over negative 2 squared minus negative 2. And if you work that out, you get 5/6. We don't really care what the value is. We care what the sign is. What is the sign? It is positive. And so, in fact, everything is positive in this interval. And you just line up a bunch of positives on that interval. Then you pick a point inside the next interval and test it. So I'll pick negative 0.5. And this would be negative 0.5 squared minus 2 times negative 0.5 minus 3 over negative 0.5 squared minus negative 0.5. And I don't have the number here, but I know that it's negative. So these are all negative. Does everyone understand why we are testing points? Does everyone understand that once I test a single point in an open interval, I get the sign of all the points in the open interval? It's because the sign cannot change in between the zeros and the discontinuities, right? Once we have all those. All right, so you would continue and do the same thing with the rest of them. This is positive. This one is negative. And this one is positive. And you would continue to pick test points for each of these. You could test 0.5 here, you could test 2, and you could test 4 for that one. Another thing that you'll see written on top of these is what they represent. So the negative 1 was a 0. So sometimes I write a 0 here. And 3 was a 0. So I'll put a 0 there. X equals 0 and x equals 1 were points where the function was not defined. So ND is what our author writes for such a thing. And now from that we can come up with the answers. The question was, where is this function positive? So f is positive on, and you just pick up these intervals. Negative infinity to negative 1, union 0 to 1, union 3 to infinity. And then f is negative on negative 1 to 0, union 1 to 3. Questions? Okay. Let's take a look at example 6. Number 6 sort of does the other thing. It says, here's a sign chart. What could be the function that had this sign chart? Of course, there are lots of answers to this, but we have all the information. So I'm just going to start. I'm going to draw the graph. Now, if you do this right, you can do it like this. Here's x equals 0, so that's the y-axis. And then we can have the x-axis like this. Let's start with the zeros and the discontinuities. Where does this function have a 0? At 1. So we know that one exactly. Remember, a 0 is also called an x-intercept or a root. So that one has to go through 0 right there. Where does this function have a discontinuity? X equals negative 2. Now, it doesn't say what kind of discontinuity it is, so you get to pick. What are your two types of discontinuities? Whole and vertical asymptote. What is your preference? You want a whole. Okay. Now, if we have a whole, we still have other options to do that as well. What's going on the left side of the whole? So we're going to say whole here. The graph is positive, so it's going to have to be up here somewhere. Then we're going to have a whole. Now, here's a question. Do you want it to be a graph with a hole and then the graph? Or do you want graph, hole, and then a jump, and then the continuation of the graph? I think we go with the second one, right? Yeah. I mean, why not? Hey, dream big, people. All right, here we go. So there's a hole. Now, the function is positive here, so I'm going to do a little, maybe an asymptote there, a horizontal asymptote. And it comes in like that. And then on this other side, we're going to have a hole. And then it's positive until what? Until it hits the 0, and then after that it is negative, and maybe it does this, something like that. We're just making it up, yeah. I mean, could this hole have been at 0? Why not? The hole doesn't have to be positive. It could, sure. Yeah, we could have had the hole at 0, and then everything around it be positive. It just comes up being positive. Okay. All right, with your partner, go ahead and create 2 excellent, aesthetically looking graphs for parts A and B. Now, these are 2 different problems, so try that with your partner. Okay. Tell us what you're doing when you do this.
Oh, these are our zeros. -3 and -1 are the zeros. And then 2 is an undefined point, which I used a hole. On the left side of -3, it's going to be negative. So let's come up to -3. And then in between -3 and -1 is going to be negative. So we would do a little U right here. And then after that, it's going to be positive, so it would go up to either a hole or a vertical asymptote. I did a hole. Then after that, it would be positive as well, so it could stay anywhere in here above.
Very good. Question? Okay, who wants to do D? Who wants to volunteer for D? You want to do D? You sure? Come on, go ahead. Your luck plus writing with a pen is basically watching those smart kids. Tell us what you're doing.
I'm putting the non-defined points first, and then our 0 is at 0, and if that's gonna, did I do something? There we go. I think it changed colors.
Click cancel at the top there. I think you hit the button. Yeah, just got that.
I put an asymptote, so go like that. It has to be positive. And then negative, I actually made a hole, or a jump. It has to go to positive after 0, and then it has to go back to negative. So, yeah.
dash line for the asymptote. There you go. Very good. Very good. All right, thank our presenters. What can you tell me about the limit as x goes to 3 per graph? What can you tell me about the limit as x goes to 3? It does not exist. The condition here was that it's positive on one side, negative on one side, and doesn't exist there. So suppose we're using a hole. Is it possible to create a graph with this still in mind, using a hole, where the limit does exist?
No.
How would you do it? Yes? No?
I don't think that the sign, because the positive and negative that exist stays just every part of the graph. Unless you just somehow converged on the 3. I don't know.
Where does the positive and negative converge? 0. That's the key. Yeah. So yeah, move this up to 0. Does this, the whole positive on this side, negative on that side. So you could do it if the limit exists. You just have to use it at 0. But but that's the neat thing. It forces it to be 0 because of exactly what you were saying. Is that it has to be positive and then negative immediately. There's only one place to do that. So,
On graph A, can there be a jump?
a jump? Sure. You could have it here and then here. Yeah, something like that. Yeah.
Could you possibly draw the other ways to do these so that we can see?
There are infinitely many ways to do this. Yeah. So, did you have something else in mind, like a different type of graph, or you're just thinking about possibilities? Yeah. I mean, there's lots of other things that you could do. A few of these things are fixed. Like this one had to have the zeros here. It had to be something down here. It doesn't have to be semicircular or parabolic or whatever. It could, wiggle and do some other stuff. But it's just got to be down here. This one has to be down here somewhere. Probably something like that. Things like that. But here, this is some freedom. This could have been a single hole, or it could have been 2 holes. It could have been a vertical asymptote, like this. As long as it's positive on both the left and the right. So there's lots of things that can happen with these. You can't really do them all. All right. Very good. All right. Last question for the day, and then don't forget we have a quiz at the end of class. Example 7. Let f of x be the piecewise function defined by the following. F of x is equal to x squared minus 1 over x squared minus x for x not equal to 1. And it's equal to a if x is equal to 1. What value of a makes the function continuous at x equal to 1? We're going to use the original point continuity for this. If f is continuous at x equals 1, then we know the 3 things, and we can actually, we can actually just write them all as one thing. The limit as x goes to 1 of f of x must be equal to f of 1. All right, I'll just write them as one big thing. So we need to force this thing to happen. The limit as x goes to 1 of f of x equals f of 1. I'll do the easy side first. What is f of 1? That's a. And then the right side here is the limit as x goes to 1 of f of x. Now, I mentioned this yesterday. When you take a limit, you do not care what happens at the particular x value that you are taking the limit to. All you care about is what's happening around that value. Well, around that value is the first piece. This is where x is not equal to 1. That's the stuff that's going on around x equals 1. So here at x equals 1, when we take this limit, we are actually taking the limit of that expression at the top. So it's x squared minus 1 over x squared minus x. If you tried to plug that in, you get 0 over 0, which is no good. So we're going to factor. So it's x minus 1, x plus 1, over x times x minus 1. What cancels? X minus 1. So this is the limit as x goes to 1 of x plus 1 over x, which I can plug in, which is 1 plus 1 over 1, which is 2. But what was that supposed to be equal to in the beginning? F of 1, which is a. So that's the answer. So what value of a makes f of f continuous at 1? The value of 2.